All right, so there's shortcut methods, but we'll talk about the origin story behind it a little bit, I guess. So f is a differentiable function, is inverse function, notation-wise, is also differentiable. That's the assumption that we have to make. And providing that the denominator is not equal to 0, then these relationships would be true, right? So the inverse function's derivative, right? So the derivative of the inverse function would be 1 over the derivative of, or the composition of the inverse within the derivative of a particular function, right? So just looking at it is very strange. At a point, I think that's easier to understand once you get a handle on what this is talking about. We're going to actually understand the relationship through this first example, because this notation, I mean, it's like chain rule gone crazy. Thank you. So let's see if we can kind of flesh this out a little bit and come up with a meaningful understanding of this rather than just memorizing a rule. All right. So, and then also in that process, come up with a justification for, why would we do it this way? Why would we use this rule when we could just do it out in, the way I'm doing it in A, B, and C here? So we'll see. All right. So f, well, let me rewrite that as just y equals, because I was about to do that in the next step anyway. So I have my function of x, my continuous differentiable function of x, well, mostly, for wherever it exists. Right? So it's a restricted domain, but wherever it exists, it's continuous and differentiable. What I want is the inverse of that. So we'll get started with that. To get an inverse, we switch x and y. And then solve for y. Right, so x squared equals y plus 2. And then y would be equal to x squared minus 2. All right. That's true and it's not true. To some extent, or mostly it's true. It's just if you look at the graph of the square root of x plus 2. So I'll just do a quick sketch. You'd have an x-intercept at -2. And then you'd have something looking like this. All right. So if you're plotting points to create an inverse graph, so we could do it just visually here, you'd have -2, 0, this point here, mapping down here to this point. So 0, -2. The x-intercept, I'm sorry, the y-intercept. The x-intercept we already had. The y-intercept you get by replacing x with 0. It's going to be radical 2. So I can plot that, or at least get a sense of it here. So this would be 0, radical 2. So that would plot to radical 2, comma 0, which I'm just ballparking would be somewhere over here. All right. So it doesn't take too much before you realize that we're not living in this world over here in the negative world for x. We're only living in the positive world for x. You're looking at something like that. All right. So my restriction would be that, because this is not, this is absolutely not in its entirety the inverse function related to this, because this would fail the horizontal line test, so it couldn't be a one-to-one relationship. All right. So we'd have to make the qualification that x has to be greater than or equal to 0. All right. That's the only instance in which that would apply. All right. So slight little adjustment. Generally something that's overlooked in Algebra 2 pre-calc. It's like, oh yeah, just switch x with y, solve for y. But this is a very important piece because the other part, if you graph this entire thing, you get a whole lot of stuff that doesn't map to the appropriate graph. Now, if this had a plus or minus in it, different story. All right, if this had a plus or minus, then you'd have the bottom half of this graph, and then these two graphs would match up to each other inverse-wise. They wouldn't be functions, or at least the inverse wouldn't be a function, but, or at least the original one wouldn't be a function. But the idea would be that they at least would match up. They would correspond to one another. But since the original function is only the top half, we'd have to account for that when we create our inverse graph. All right, hopefully that made sense. All right, so the derivative of f of x. Derivative of f of x. So I'll rewrite f of x as x plus 2 to the 1/2. And then we'll take the derivative of that. So f prime of x would be equal to, this one's not bad, 1/2 x plus 2 to the negative 1/2. All right. Also, just going back to a for a second, we'd want to rewrite that using the proper notation. Because in theory, I mean, I guess everything is a y. This is specifically the inverse of the original function. Inverse function of the original function. All right. So, what I would be looking for, just kind of going back here to this expression, I'd be looking for the derivative of my inverse function. So just kind of following along with example A, we can continue that progression. Find that derivative. You know, the derivative would just be a 2x. All right, so if I needed the derivative of the inverse function and I didn't have a rule to work with, what I would have to do is find the inverse function and then take its derivative. Sometimes that's easier to do, sometimes it's not. All right, what we're asked to do here is verify or make sure that this is the correct relationship so that in the future, if I needed to or if I wanted to, I could use this relationship. If you look ahead in the packet, you see some table-based problems. They're really interesting to look at, but these are very popular AP style questions. They're on page 70, and you could see it's a table. It's got information about functions, derivatives, and things like that. And so, working with a table numerically is something that they're going to ask you to do, and that lends itself very nicely to this relationship. All right. So, what do we want to do? We want to find this piece here and see what's going to come out of it. So the derivative of my original function composed with the inverse. All right, so I'll just start with that. So in part C, f prime of the inverse. All right, we learned in Algebra 2 that when you're composing functions, you're plugging one into the other, so we're taking the inverse and plugging it into the derivative function, derivative of f of x. So 1/2 x plus 2 to the negative 1/2, and then I'm plugging the inverse into that. All right, and the inverse is x squared minus 2, again with the condition that it's only positive values. I think I already forgot. Was it minus 2? Yeah. All right, so we're looking at 1/2 of x squared to the negative 1/2, which would be 1 over 2x. Now, what the relationship is telling us is that the derivative, undo. The derivative of the inverse of x should be equal to the reciprocal of what we just figured out. So the derivative of the inverse, let's try that again, shall we? So that, which we know is 2x, should be equal to 1 over the derivative and the inverse composed. So 1 over 2x. And those are the same thing, all right? 2x and 1 over 2x would be the same thing. So it checks out. So we have a working relationship here. So we want to be able to use this, and the idea is not to have to do it out both ways at the same time, obviously. And also the idea is not to have to do it out algebraically. The idea is to be able to use this relationship so you can apply it to numerical situations. All right, so we're going to use the right-hand side, well, really in this case because it's at a particular point, to determine some useful information. All right, so looking at number 2, it asks us to determine, okay.
So
Yeah.
like back at the top, so there's like 2 ways to do it. Either you just take the inverse and take its derivative, or you take the inverse and then take the derivative of the original function and then plug the inverse into the derivative. That's all.
Correct.
You're saying, but sometimes that might, even though that sounds like it might be more work, it might be easier?
Yes.
Okay.
Okay, so the interpretation of what the notation means is going to make all the difference, I think, anyway. So, this part. The inverse function evaluated for when x is equal to 0. All right, so I'm just gonna write out what it means. All right, so it means evaluate, I'm going to try to write it correctly, using like grammar and spelling and stuff. Evaluate inverse function when x is equal to 0. Okay. So when you're living in the world of inverse functions, the bizarro universe, everything's swapped. Everything just got reversed. All right. So you're looking at, in the inverse function, if you're evaluating the inverse function when x is equal to 0, that's the same as evaluating the original function when y is equal to 0. All right, because domain becomes range, range becomes domain, x becomes y, y becomes x, x-axis, or x-intercepts, or y-intercepts, y-intercepts, or x-intercepts. Everything gets reversed. All right, so if we're looking, if this notation is telling us to find y in my inverse function when x is a particular number, that's really the same as saying in my original function, find x when y is a given number. All right. And what that allows us to do is avoid the process of actually finding the inverse function. We can work with the original as is. All right. So I'll show it both ways because a log function is very easy to work with. So I have y equals ln of x. All right. Now the inverse. Would be y equals e to the x. All all right? Because we would switch the x with the y and solve for y, all right? So I would make this x equals ln of y, and then I do my hocus pocus, and I would get up with this equation here, all right? So then, if I want to evaluate the inverse function when x is equal to 0, that's saying, okay, plug in a 0 for x. All right, but and that would give us a 1. And that's all well and good. But it required you to come up with the inverse function to begin with. You think of a bunch of different circumstances where you're given a function and it's either not possible or not practical to come up with the inverse of that function. All right, I'll give you one right now. You can very easily switch the x with the y, right? Not a problem there. It's the solving for y part that would be the problem. All right. So a lot of different cases where it's not going to be either possible or practical. All right. Now, if I'm telling you that doing this is the same as replacing the y with a 0 in my original function and solving, then that's a different story, all right? Because now we're working with something numerical, right? Now, even though it ends up being the same calculation, really, in this context, here it's massively different. It goes from being impossible to possible, right? Because now if I replace the y with a 0 here, I can use rational root theorem. I could use rational root theorem. I can't think of anything else that I would do initially besides that. Maybe create the graph or something along those lines, but I would not have to worry about algebraically getting this equation solved for y in terms of x after I've switched the x with the y, right? So the benefit is really in this aspect of it. Something that is either impossible or impractical to find the inverse of, right? But either way, we're gonna get a 1, all right? So our answer to part A is equal to 1. All right, so now part B relies on our new rule, our beautiful new rule. All right, my line draw tool thingy isn't working anymore. Or at least I'm not functionally able to make it work. So if I want to find the derivative of the inverse at 0, I want to find this relationship. All right, and we'll do it a piece at a time. All right, so the first thing I would do is figure out what the inverse at 0 is. Well, fun fact, we already did that, right? That was a 1. Then I would want the derivative of my original function at that particular number. All right, so I go to my original function. F of x equals can't even speak anymore. It's like the week needs to be over. The year needs to be over. Like the calendar year, not the school year. I'm fine. Well, I suppose the school year also, but but for me, it's not like it ever ends. Like this school year ends, the next one begins 2 months later, and it's a perpetuating cycle. It's actually pretty depressing when I think about it that way. So, I'm going to stop talking. So the derivative of my function f of x is 1 over x, because that is the rule for natural logs. And so I want the derivative at the x value of 1. So 1 over 1 is 1. And so at long last, if I'm looking for the derivative of my inverse at 0, I have everything I need. 1 on the top, this guy on the bottom, so the result would be equal to 1. All right, but number-wise, not too bad. Algebra-wise, be pretty crazy, I think.
I'm a
or could be pretty close.
Why, when you take f prime, you take it at 1?
Because it's f prime of the inverse at 0. So the inverse at 0 is 1. So it's f prime of that result. All right, so when all is said and done, we're talking about, I mean, if you're going to commit one to memory, it's going to be this one, right? And that's because it's the one that's most applicable, because algebraically, I mean, that's just to prove it really, this is really the one that we care about, the one that's at a particular point. All right, so we already did in part A, we already did the inner part here. So this is calling for us to figure out the derivative and then plug in the answer that we got for part A and then go from there. All right, so yeah, it's a really weird topic. I like it for the sake of, you know, math is fun and I like to talk and learn about math. I teach it because for whatever reason they love putting a problem like this on the AP exam. I don't know that it necessarily furthers the cause of understanding of calculus, but it'll help you get a question right. So yeah, that's good. But yeah, it's something that's kind of hit or miss depending on the nature of the function, because you get to something like f of x equals arctan of 3x. If you don't know what the derivative of that is, then all bets are off. This rule is going to fail you, right? You need to be able to find the derivative of your given f of x, right? Otherwise the rule breaks down. The alternative to that would be to actually find the inverse of it. Now the good thing about an arctan is that it is by definition an inverse function. So we already know, we have a sense of what the inverse of that is going to be, because just based on the very name of it. So it's the arctan, so its inverse would be it would be tangent of something. It's just a question of, will it be tangent of 3x or some other constant multiple? You'd have to flesh that out. But if you do know the derivative of arctan of x, the arctan of u rule, then you're all set. All right, so the progression here again is to find the inverse at 0. So f prime of inverse at 0. So again, we don't want to actually find the inverse function. All I want to do is replace my y with 0 and solve for x. And don't get me wrong, I mean, in the solution to some of these problems, you will most likely be using inverse skills. It's just you're not getting an algebraic expression that represents the inverse function. All right, that's the important piece. Yeah, so in my next step, what am I going to do? I mean, I might reason out what the arctan of 3x would be if I happen to really be strong with the unit circle. But odds are you're going to say, okay, well, I'll just take the tan of both sides, which is what you would do if you were going to find the inverse of it anyway. So tan of 0 equals 3x. What is the tangent of 0, by the way? 0. And so we get x equals 0. All right. So the inverse function of x at x equals 0 is equal to 0. And in part B, they want me to go the distance, but at this point we kind of know better, know enough to say, and again, it's just reflecting back on that rule. Derivative of the arctan of 3x would be what? Nine x squared, yeah. All right. So I'm looking for the derivative of the inverse at 0. Bless you. So f prime of this, which would be the same thing as f prime of this, because that's what we just figured out in part A, which is just telling me to plug in a a 0 for x here, and when I do that, what do I get?
3.
You get a nice 3. All right. And so to answer part B, all I have to do is take the reciprocal of that. All right, because the rule has us doing 1 over the derivative of the inverse at the point. All right. Just once you understand the rules of the game here, it tends to get a little bit easier, but it's definitely not. That's something that is. It didn't come to me naturally. I was looking at that rule and be like, what do they want us to do and why? So, in part A, inverse function at radical 3 over 2. So if I plug in a radical 3 over 2 for x in my inverse function, that's the same as plugging radical 3 over 2 in for y in my original function. All right, unit circle magic. Now, if I were to find the inverse of the sine function, I would get what function? This is an easy question. The inverse of the sine function? You'd get the inverse sine function, yeah. Or the arc sine, if you want to call it that. But I was going for inverse sine because that was more fun to say. But anyway, if that's the case, I'm restricted in my interval. My domain for my sine function has to correspond with the range for the inverse function. So the range for the inverse function for sine has to be between what and what? Negative pi over 2 and pi over 2. All right. Cosine, arc cosine is between 0 and pi. Sine is negative pi over 2 to pi over 2. So with that in mind, knowing that I can only be in fourth quadrant or first quadrant, what must be the angle that gives a sine ratio of radical 3 over 2? Pi over 3. All right, so I now know that the inverse at radical 3 over 2 is pi over 3. All right, so then I need my derivative, f prime of x, nice easy cosine of x, which I think is what, when I asked for inverse, before somebody said cosine, I think they heard derivative when I said inverse, and that's totally fine. It happens to the best of us. All right, so I need the derivative at the inverse of radical 3 over 2. So the derivative at pi over 3, which would be what? So what is the cosine of pi over 3? 1/2. All right, and so my final answer, so my B, the inverse's derivative at radical 3 over 2 should be what? A 2. Now, number 5 gives it to you in table form, and assuming I fixed the typo from the last decade, it should be good. It shows differentiable functions of f and g, so it gives us the derivative, the function and the derivative at particular points. So it gives us everything we need to know about functions, inverses, derivatives, and their inverses. So it's just a matter of kind of picking out what the hell the question's asking.
Why in that one did we take the reciprocal of 1/2, and then in 3, we got the answer is 3? Oh. That way it sinks.
All right, so they're saying H is equal to the inverse of F. So they want to know H prime of 2, all right, whoever they are. This is going to be way simpler than what I was about to do. Boop. Boop. Couple of boops. Totally. Right? So if I'm taking the derivative of this, that'll give me the appropriate form, and all I'd have to do is take the derivative of that in order to get the appropriate form. It looks subtly different from the way that they were expressed previously, but it is essentially saying the same thing. The inverse is derivative. The inverse is derivative, all right? So add specifically 2. So what I would need, and I would just follow the progression, I need the inverse of f at 2. All right, so again, just thinking about it, it's telling me to figure out the x value in the original function that has a y value equal to 2. So the x value in the original function of f that has, so I'm in the realm of f here, has a y value of 2. The x that goes along with that would be 1. All right, so then what I want to do is find the derivative of that 1. What would be the derivative function at the x value of 1? 3. All right, so we're going from here to here. And then the final step would just have us taking the reciprocal of that. So h prime of 2 would be equal to 1/3.